All right, so we're going to continue our discussion of transformation of some functions. So we are on section 223 of our CPM textbook. So we've been talking about moving our functions, and I'm so confused. Why is it saying that? What does that mean? Please move this window away from the shared application. Well, too bad. I'm recording the book. Whatever. We're moving on. All right. So, where was I? Clio High School. We've been talking about those transformations. And in geometry, when it came to those transformations, we like to call them translations, which was moving them to the left or to the right. Reflections, where you were flipping it over an axis or over a point. Rotation, you guys did some 90-degree rotations and 180-degree rotations, those types of things, and probably a rotation of 270. And then dilations, where when you would shrink something or make it bigger, right? You would change the size of it, kind of like your pupil when it dilates, it gets bigger or smaller. So when it came to us working on our families of functions and translating those, I mean, those kind of were some of those same kind of maneuvers that were going on. So just as a little refresher over everything like we kind of been doing, when we took our function, well, maybe, right? And we did the plus k on there, right? So the k, or whatever the variable or the letter number was not part of the x. That's when we shifted it up or shifted it down. Remember that good stuff? If we had where it was with our x somehow or another, regardless of what family of function it was, since it was with x, it moved it along the horizontal axis. So our h is telling us if we're moving it left or to the right. And if we had a number out front, if it was negative, it flipped it over the x-axis. And then if it was a number greater than 1, it stretched it because you were getting there faster. And if it was between 0 and 1, you got there slower, so it compressed it, so it took you longer to fill up that spacer to get there, right? So we've talked about left and right, up and down, and flipping it over the x-axis, and then shrinking and compressing. So today, we're going to do a little Desmos activity and then a little algebra activity, where what happens if wherever our x is in the equation, if that x became negative, what that would do to our nice little function. So we're going to jump over here to Desmos, because we love some Desmos activity. And I don't know, let's start with, we've been having fun with quadratic, so let's stick with the quadratic. So if we had x squared. So they want to know if we take our original x squared, but wherever there is an x in the problem, we change it to a negative x. So we would then have the quantity negative x squared. So when I put that negative onto that little x, make a conjecture. What do you think would happen to that graph? It's gonna what? It's gonna get bigger. Anybody else got anything they wanna? I know you're thinking it in your head, you just don't want to say it. All right, you ready? Close your eyes. Open them. So that was our original x squared. And when we made it the quantity negative x and we squared it, what did it do to it? It didn't do anything to it. It stayed exactly the same. Oh, we'll try that. We'll try cubing next, right? So on this one, when we put that negative in there, it didn't change it. we'll do some problems algebraically, but if we think about it algebra-wise, if I were to simplify this negative x squared, that's negative x times negative x. What's negative x times negative x? X squared, right? So we really didn't change the problem at all. And one thing they say, it's like, if I take this graph, it's called symmetric around the y-axis, because what is on the left side of the y-axis is exactly the same that's on the right side, right? Right. So somebody said to try this with to the third. So I'm going to take the negative out of there. Can't give you the answer yet, right? So it's the same one. So we have x to the third, which gives us this cute little cubic, right? It's cubic, so, or to the third, so one end goes one way, one end goes the other way. And on this guy, if I put a negative out front, what do you think is going to happen? It's going to move it down. Anybody else got anything? Boom! So that was the original. I'm going to make that just a tad bit bigger, right? Just so you can see the colors a little better, right? That was the original, the black one. Then when we made it negative, what did it do? Ooh! Yeah. So on this one, if we were to simplify negative x to the third, right? Negative x times negative x would have given us a positive x squared, times another negative x would have given us negative x to the third. So technically it flipped it over the x-axis, right? If we were to simplify it all out. Or we could say that it even technically reflected it around the y-axis. Because if we start with the black, this was originally on the right, and then what did it do? It flipped it over to the left. Okay. This was originally on the left. What did it do? Flipped it over to the right. I got some more for you. Oh, that's not what I want. What if I had 1 over x? So 1 over x, if we think of our domain, because we're like, why does it look kind of funky? Like, why do I have this little swoop on one side and a little swoop over here on the other side? Well, what do we know about denominators? They can never be 0. So since our x is in the denominator, we can never have it when x is 0. So it creates that funny little line called the asymptote. Good job, right? And then we know also that like our value, we can never get this to equal 0. 1 over nothing is going to give us 0. So we also know we have an asymptote, a horizontal asymptote as well. So we got a vertical one and a horizontal one. All right. So they want us to take our little function, and wherever there's an x, they want us to put in a negative x. What do you think is going to happen with that one? You ready? Here it comes. Whoop. So that one reflected it as well, didn't it? All right. What if we had x 1 over x to the 4th? So 1 over x to the 4th gives us this funny little, that's a logo somewhere. I know it is, and I can't think of what it is. Or close to it. So if I take my x, just my x, and wherever there's an x, if I make it a negative x, what do you think is going to happen? You got any ideas? So far we've either left it the same or we flipped it, right? What do you think? You ready? In 5, 4, 3, 2, 1. Boom. So that was the original? When we put the negative in there, it stayed the same. Right? Look at you, yep. So if it's even, it stays the same, and if it's odd, it's going to reflect it, yep. And if we look at our exponents give us a big clue on that too, because that's a even exponent. We know that it's going to stay exactly the same, yep. And then just for some poops and giggles, if we had the square root of x, right? And if we made our x negative, what do you think it's going to do? Stay the same or reflect? Oops. Reflects it. Okay. Very cool. All right. Ready to try a little one algebraically? Let's play around with some numbers now. Why, of course you kicked me out. It wouldn't be any better. Let me sing for you. Oh, solo mio. Let me play with my screen. All right. So what we learned from doing our little Desmos activity is, so on that first one, we started off where f of x equaled x squared, right? And then we compared it to where if we took f of x and we put in a negative, so then we had negative x to the squared, and we simplify that and we got x squared. And then what we noticed was the original f of x and then the new f of negative x, those guys stayed the same. They actually became the exact same graph. It didn't change it at all. So we call these ones even functions. I think I can get it fit there. Ooh, close. Okay. And then we decided to explore a little farther, and we did f of x equals x to the third. Then we decided to make f of negative x. So everywhere there's an x, we put in a negative x. And we simplify that guy down. And we got negative x to the third. So now if we look at our original and then our new negative x, we notice that the sign changed. And if our signs all change, we call that a odd function. And when we actually look at graphs of these, oh boy. I wonder if I can. So we know that this one's going to be odd. So ultimately we say that it reflects over the origin if it's odd. So when I look at this graph, if I go from the origin and if I go up to try and find a point, that distance is the exact same if I go in the opposite direction from the origin. If I come down, right? So it's actually reflecting it over like that identity line in a sense. So if I go from here to here, and if I go from here to there, it's like that same thing. That's where that symmetry comes in. Where if I am squared, right, I have whatever is on the left side of the y-axis is on the right side of the y-axis. All right. So we just kind of kept these nice and easy and pretty, but sometimes in life it gets a little messy, right? And maybe they want to give us a little bit more advanced of a function. So let's say they gave us something like, oh, I don't know, let's go with f of x equals 2x to the third minus 3x squared minus 4x plus 4. So we want to know if it's even or odd, and guess what, there's a third choice, neither. Right? So our evens, we know what's on the right side of the axes. The y-axis is going to be the same on the left side of the y-axis. If it ends up being odd, we know that from the origin, it's going to be completely symmetric, going in opposite directions. And neither is just one of those wah, 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 wah kind of graphs. So to test it, what are we going to do? F of, yep, negative x. Good job. Proud of you. So we have what? 2 times negative x to the third minus, I'm going to squeeze this down a little bit. I have all this room. F of negative x. So 2 times negative x to the third minus 3 times negative x squared minus 4 times negative x plus 4. And then we're just going to simplify our x's. Okay? So f of negative x equals negative x to the third. Negative x times negative x times negative x is going to give me a negative 2x to the third. Negative x squared is going to give me a positive x squared. So then I'm going to have negative 3x squared plus 4x plus 4. Right? So I want to go back from and look at my original, and I want to look at each one of these terms. So when I look at this first term, that one's positive, and this one's negative. So we're like, oh, I'm getting all happy. I bet you this is going to be odd. But then I go, oh, I got to keep going. And then I check the next one. And when I check this next one, I have negative 3x and negative 3x squared. And you're like, well, darn. If they're the same, that means they're even. So my first term's telling me it's odd, and my second term's telling me it's even. I don't know which one to pick, so I'm going to pick neither. And if we were to graph this guy, he would be the original, right? 2x to the third plus 3x squared minus 4x plus 4. Shrinky, shrinky, shrinky. Whoop, maybe. Yeah, a little bit. We'll go to there, right? All right. So what did we come up with? If it was even, it would be the same thing that's on the left of the y-axis is the same thing on the right is the same the y-axis. Is the left identical to the right? No. And then the other one was, if you look at the origin, and if I go from the origin and I go to any point, so let's say I went this way, right, then I should be able to go the opposite direction and get that same matching point. And does that happen? No. So then we know then that our function is not odd. So it's not even or odd, it's neither. So we know that there's no symmetry to our function. So these are all little things that can help us when it comes to being able to graph these guys. Okay. Sometimes when they give you the problems and they want you to tell me or tell yourself if they're even or odd, they might tell you like y equals like x plus 3 squared. Oops. I gotta switch back. Sorry guys. There we go. So y equals x minus, or x plus 3 squared. So to check to see if that has symmetry or if it's odd or even, you're putting in that negative, right? So instead of the original f of x was x plus 3 squared, and we need to try f of negative x, so that equals negative x plus 3 squared. So to test it, you can't tell anything the way that it is with that being squared, so you guys got to square these out. So, because this is the same thing as x plus 3 times x plus 3, right? This is negative x plus 3 times negative x plus 3. So whatever is your preferred method of multiplying these factors out, some people like to do that area model, right? So this would give you x plus 3 and x plus 3. So x squared plus 3x plus 3x plus 9. So my original is going to be x squared plus 6x plus 9. Okay. Some of you guys like to use the FOIL method, right, where you're distributing everything with everybody because sharing is caring. So we would have x squared minus 3x plus 9. So that would give us x squared minus 6x plus 9. And then now you're going to compare the signs. Sometimes some people even write them out. This one goes positive, positive, positive. This guy goes positive, negative, positive. Are all the signs exactly the same as what they originally were? No. Do they all switch signs? No. So this would be another sign of, or another example of neither. So if they give you guys the problem where there's these factors, make sure you're multiplying them out.